All right, so we're in part 2 of 15.6. So we're going to talk about surface integrals on vector fields. So the first thing we need to talk about today is when we're talking about surface integrals with vector fields, we're dealing with what we call an oriented or orientable surface. So we need to talk about what an oriented or an orientable surface is. The informal idea, the kind of working definition of an oriented surface is that it has two sides. And because it has two sides, it has two normal vectors at any point. So if we're looking at it, just a quick sketch of what we're talking about, here's our surface. We can, at any point, we have a normal vector this way, and we also have a normal vector this way. So this is what makes an orientable or an oriented surface. And if we were being a little more formal about it, we would say that a surface is orientable or oriented so we can define a unit normal vector at any point on the surface, and our unit normal vector varies continuously over the surface. So we have a nice surface. It doesn't do any strange things, and we'll talk about a couple of strange surfaces at the end. I have them stacked up on the paper or on the table there. So an orientable surface, we can define a unit normal vector anywhere on the surface that varies continuously over the surface, and it has two sides. So we have an upward. If we think of our surface, we have an upward normal vector and a downward normal vector. So for a smooth parametric surface, so if we have R of U and V, our unit normal vector, N, is going to be our cross product of our partial derivatives divided by the magnitude of that cross product. So this is nothing really surprising about a parametric surface. We've found unit normal vectors for surfaces before doing this exact thing. And then negative n would be the unit normal vector in the opposite direction. So those are our two unit normal vectors on our point on an orientable surface. So if we have our the type of surface that we've been working with more frequently, if we have z equals some function of x and y, what we do to come up with our unit normal vector, and we've done this before, is we write g of x, y, z equals z minus g of x, y, and that equals 0. And to find a unit normal vector for this surface, what do we do? For a function where we have a surface g of x, y, z equals a constant, what gives us a normal vector?
Cross product.
We talked about it just the other day.
I'll let you know.
You remember, Paul? You came up with the answer then. The gradient.
Yeah.
Our unit normal vector is going to be del g over the magnitude of del g. So when we have a surface g of x, y, z equals a constant, the gradient gives us a normal vector. So if we divide the gradient excuse me, by the magnitude of the gradient, we have a unit normal vector. And again, negative n is the unit normal vector in the opposite direction. So in this case, if we have our surface g of x, y, z, we can write out del g. Del g equals minus dg dxi minus dg dy j plus k. Because I wrote my surface, the equation of the surface z minus g of xy. So when I take the partial derivatives, these two components will be negative. We call this the upward unit normal vector. So this would give us our upward normal vector. We have to divide by the magnitude to get the unit vector. And we call it upward because the k component is positive. So this is our upward unit normal vector, and minus del g is the downward normal vector. Because our signs would change and the sign on our k component would be negative. So del g, if we write our surface as g of x, y, z equals z minus this function, the gradient of that function gives us our upward unit normal vector. And it's going to play a really important role when we're talking about our surface integrals. So now we know what an orientable surface is. We know how to find a unit normal vector on our orientable surface if we have a parametric surface, or if we have our surface written z equals g of xy, which is how we've been working with surfaces for the most part this semester. So now that we have all that, we're ready to talk about surface integrals on vector fields. We want to start with the idea of flux. So we're going to have some orientable surface S. So this is our surface. And we say that S is an oriented surface And f, our vector function, is going to be some velocity field here. So we could think of liquid, if we wanted to, liquid flowing across that surface. So there's f, and we're going to say f is a velocity field. And we're using a velocity field to develop this idea of flux. It does our field doesn't have to be a velocity field. We're just using that to talk about our idea. And we have a normal vector, a unit normal vector at this point on the surface. So this is going to be, call that n, our unit normal vector. And we're going to consider a small little piece of area on this surface. And we'll call the area of that little piece where our field is flowing through the surface, we'll call that the area delta S. So the volume of, if we think of a liquid, something flowing through the surface, and F is the velocity field, the volume just adding some detail here. N is our unit normal vector, delta S is the area. So the volume of the liquid that flows through that little piece of surface is going to, per unit time, is going to be F dot N times delta S. F dot N gives us, if we think of the liquid, a piece of the liquid flowing through that surface, we would get an oblique prism, kind of an oblique prism shape of the liquid that's flowing through the surface. And F dot N would be the height of that oblique prism. So F dot N is the height of the prism, delta S is the area of the base. So the volume per unit time that flows through the surface is F dot N delta S. We call this the flux. F dot N delta S, this volume is the flux. Now what we're going to do is assume that delta S is so small that F, our velocity field, is constant in that little piece of area. So we're making delta S very small. And we're assuming that delta S is a parallelogram. So it's very small. The field is constant there. Delta S is a parallelogram. And F dot N delta S is the area or the volume of that small oblique prism on the surface. And what we're going to do is sum this quantity, F dot N delta S, over the entire surface and take the limit as delta S gets very small. So this is an argument that we've used over and over again. So we're going to take that volume at each delta S on the surface, sum that over the surface, take the limit as delta S gets very small, and we define our flux integral. We're going to sum over the surface as delta S becomes very small. And that gives us our surface integral of the vector field over S, over our surface, or our flux integral. And the flux integral is, we're saying the same thing as the surface integral of f over the surface. Surface integral of a vector field is the flux integral. And we're going to define that as the double integral over our surface of f dot n ds. And we call this the flux of f across f. Or sorry, across s. So this is how we're going to, this is what our double integral or our surface integral of a vector field is going to be. We're going to sum the normal component of f over the surface. That's what we're doing here. So the surface integral of a vector field is the integral of its normal component over the surface. Now we need a way to evaluate this flux integral. This f dot n delta s, or f dot n ds. Well, we have a nice way that we can simplify this integral so we can evaluate it. So here's what we're going to do. Any questions before we move on about our definition of the flux integral? So again, we're summing the normal component of f over our surface. All right. So if z, our surface, is given by z equals g of xy, that's what we've been working with for the most part. Then we're going to say g, capital G, of xyz is z minus g of xy. Just like we did when we were talking about our unit normal vector. Our unit normal vector, n, is del g over the magnitude of del g. So there's our unit normal vector. And ds on this surface is the square root of g sub x squared plus g sub y squared plus 1 dA. So if we have our surface given by this, then this is our little area, our little increment of area on the surface. Well, what is this quantity, square root of g sub x squared plus g sub y squared plus 1? Anybody see what this is? Let me go back. This is the square root of the components of del g squared, which is the magnitude of del g dA. So what we have, so our flux integral, so the double integral over our surface of f dot n ds equals the double integral. I'm going to put r because we have a dA here, we have a region in the xy plane. F dot n, f dot del g over the magnitude of del g times the magnitude of del g dA. And these magnitudes of del g cancel, and we get that this just equals the double integral over our region in the xy plane now of f dot del g dA. And we've taken our unit normal vector with upward orientation. because z is positive. So this is with the upward orientation. So this is how we're going to evaluate this surface integral of this vector field. We have to write this process. What our expression only works if we write our surface in this form, z minus g of xy. Then our surface integral of our vector field over the surface is f dot del g dA over our region in the xy plane for our surface. So this is how we're going to, for the most part, this is how we're going to evaluate our flux integral, f dot del g dA. Questions on that? Yes?
So if you have something that's already a function of x, y, and z,
So we'll talk about that we'll do an example where that's the case. Okay? And we'll get to it then. All right. If we have our surface as a parametric surface, then our unit normal vector we said was RU cross R sub B over the magnitude of RU cross R sub B. And ds, in this case, we talked about this before. Our surface, our little increment of surface area is the magnitude of R sub u cross R sub b dA. So in this case, our double integral, our flux integral over S of f dot n ds is going to be the double integral over our region in the xy plane of f dot R sub u cross R sub b dA, and R here is a region in the UV plane. So this is going to be how we evaluate our flux integral if we have z equals f of xy, and this is how we're going to evaluate our flux integral if we have a parametric surface. So questions on what a flux integral is? Okay, let's evaluate a couple of these. So for our first example, we want to find the double integral of S of f dot n ds. So another way that this problem could be asked is find the flux of f through s. So we're finding the upward flux of f through s. These two things mean the same thing. F is given by our vector field is xi plus yj. And s is 2x plus 3y plus z equals 6 in the first octant. So because we have everything in terms of x and y, and here we have f of x, y, z equals a constant. So I could write z equals 6 minus 2x minus 3y. but it's already given in terms of f of x, y, z equals a constant. So we're going to, in this case, we're going to evaluate f dot del g dA, and we're saying that g is just 2x plus 3y plus z minus 6. So g equals 0. So we need our del g. So the gradient of g is going to be what? And f dot del g for our integrand is just going to be 2x plus 3y. And this should be r for our region in our xy plane. All right, now we need to find our region in the xy plane for our limits of integration. So this, what kind of surface is this? A plane, and we want to find where it intersects the first octant. So what's our region going to end up being? A triangle. We end up with a triangle in the xy plane. So sketch it out really quick to find our region. If you worked on last night's homework, you did a couple of these. So to sketch a plane in the first octant, I'm going to let x and y equal 0, y and z equal 0, etc., and find where they intersect the axes. So I get, this is z equals 6. I get x equals 3. And over here at y equals 2. Yeah, the scales on my axes are different here. I was taking into account perspective. Opposite. Yeah. All right, so there's our where our plane intersects the first octant, and for our region in the xy plane, we need the equation of that line. We have 2 points. We have the y-intercept. We can figure out the slope, so it's not hard to find the equation of that line. That's y equals minus 2/3 x plus 2. So my region, R, is 0 less than or equal to x less than or equal to 3, and 0 less than or equal to y less than or equal to minus 2/3 x plus 2. So those are my limits for my double integral, and we're set. So our integral of s over s of f dot n ds is the integral from 0 to 3, the integral from 0 to minus 2/3 x plus 2 of 2x plus 3y dy dx. So nice, easy integral to evaluate. Just polynomials. We end up with just polynomials in our integral. When we evaluate this, this comes out to be 12. So if we think of this as a liquid flowing through the surface, there would be 12 units of this liquid per unit time flowing through the surface. And our process here: find del G, express our surface as f of x, y, z equals 0. Find del G, find our region in the xy plane, evaluate our double integral over that region of f dot del G. All right. Let me talk quickly about the question that that Star asked. What if we don't have f of z is as a, what if we already have z is f of x, y, z is some function? So what if our surface, I'm not going to go through the entire example here, but what if our surface was given by x squared plus y squared plus z squared equals 36 in the first octant. And we needed to evaluate a flux integral, and this was our surface. Well, we have some function of x, y, z equals a constant, right? But in order to use the expression, the double integral over r of f dot del g, we said that g of x, y, z was z minus g of x, y. Our surface, we have, in order to use this notation, this expression, we have to express our surface as z minus g of x, y. That's what gives us our upward normal vector. So in this case, I would not say, I would not just take the gradient of this directly to find my normal vector. That wouldn't give us the proper flux integral. So in this case, I would say z equals the square root of 36 minus x squared minus y squared. And so g equals z minus the square root of 36 minus x squared minus y squared. So this would be the quantity that I would take the gradient of to find my normal vector. Does that help, Star? So in order to use, this is a place where a lot of students make mistakes here, is in order to use this expression, we have to write our g of x, y, z in this form in order for this expression to work the way we want it. All right, let's do one more example, and we'll be done. And then we'll talk about all the stuff that's on the table here. We want to find the flux over the closed surface. And we want n here to be the outward normal vector. Our field is x plus y I hat plus y j hat plus z k hat. And our surface is z equals 1 minus x squared minus y squared, and z equals 0. So what is this surface going to be? Is it spherical?
No.
You're close. Z isn't squared, so it's not spherical, it's parabolic. This is going to be a paraboloid. So I have an inverted paraboloid. So I'll sketch it in the first octant here. The sides are parabolic. This. In the xy plane, it's a circle. So this is v equals 1 minus x squared minus y squared. Here in the xy plane, we have x squared plus y squared equals 1 when z equals 0. And this is a quarter of our surface. All right, it wants the flux over the closed surface. So we have to take into account two different things. So the top surface is our paraboloid. What's the bottom of the surface? It's a circle in the xy plane. So we have to find the flux outward through the top here, and we also have to find the flux outward through the bottom. It wants the flux outward over the entire surface. So we have two parts to take into consideration. So we want to figure out how much of this field is flowing out of the surface here and out of the bottom here. So let's look at the bottom first. What would be the outward unit normal vector on the bottom of this surface? Negative k hat. This is easy. The outward unit normal vector is negative k hat. Sorry, that should be an n. Our unit normal vector is negative k hat. F dot n is, take the dot product of this with negative k, is just negative z. So we're integrating for the flux along the bottom. We're integrating the integral over r of negative z dA. On this circle, what is z? 0. So what's this integral? 0. Z is 0, so this integral evaluates to 0. There's no flux out of the bottom of this surface. And if we look at our field, when z equals 0 in the xy plane, there's no k component of our field, so there's none of the field is flowing across the surface at z equals 0. So on the bottom, the flux is 0. So now we just have to worry about the top. So on the top, G, capital G for our surface, so we can find our normal vector is z plus x squared plus y squared minus 1. Del G gives us our normal vector. Del G, in this case, is going to be 2xi plus 2yj plus k hat. So we have our upward unit normal vector. F dot del G. For our integrand, when we take the dot product of F dot del G, I get 2x times x plus y from my I component plus 2y squared for my k component plus z. And if I simplify this, I'll expand this out and simplify. I get, and before I simplify, I'm taking the double integral over our region in the xy plane. So what are we going to use for z here? One minus x squared minus y squared. So we're taking the double integral. Our double integral in the xy plane is only going to be in terms of x and y. So z is 1 minus x squared minus y squared. That's our surface. So I'm going to substitute that in for z and simplify this. When I do all of that, I get x squared plus 2xy plus y squared plus 1. So that's going to be my integrand. And we're integrating over the region in the xy plane. Our region is a circle in the xy plane, so how are we going to want to evaluate this? Polar coordinates. We'll use polar coordinates. So we're going to change this to polar coordinates. We're going to switch the, I'm going to go to the next page here. But we're going to evaluate this integral in polar coordinates. So in polar coordinates, f dot del g is r squared plus 2r squared sine theta cosine theta plus 1. So I'm just substituting for x and y in polar coordinates. And our integral we have the integral in the first quadrant, theta equals 0 to 2 pi. Oh, sorry. In the first quadrant, it would be pi over 2, but we're doing the whole thing. I drew a quarter of it. Yeah. So in the picture, I just drew a quarter. R equals 0 to 1, and our integrand, r squared plus 2r squared sine theta cosine theta plus 1 r dr d theta. I forgot a theta here. Right, on the bottom it was 0. So this is the flux out of the surface. Not a difficult integral to evaluate here, because we have the sine theta cosine theta. We have a u sub there. So this integral is not a difficult one to evaluate. Nothing tricky. This evaluates to 3 pi over 2. So the flux out of the paraboloid is 3 pi over 2. Yes.
So this is basically the divergence in some of the
This would turn it's a sum of the divergence of what the divergence theorem will tell us is it's a sum of the divergence of the field through every volume element on the interior of the solid is the flux out of the surface. That's what the divergence theorem, and we'll talk more about that on Monday. All right, questions? All right, before I give you your homework, I want to talk about these Mobius strips that I have here. In your book, it asks there are a couple of questions about a non-orientable surface. Here, let me just stop this.